Chapter 8, Principles of Security Models, Design, and Capabilities. The CISSP exam topics covered in this chapter include Domain 3.0, Security Architecture and Engineering. 3.1, Research, Implement, and Manage Engineering Processes using Secure Design Principles. 3.1.4, Secure Defaults. 3.1.5, Fail Securely. 3.1.7, Keep It Simple. 3.1.8, Zero Trust. 3.1.9, Privacy by Design. 3.1.10, Trust but Verify. 3.2, Understand the fundamental concepts of security models. For example, BIBA, STAR model, Bell-LaPadula. 3.3, Select controls based upon system security requirements. 3.4, Understand security capabilities of information systems, IS. For example, memory protection, Trusted Platform Module, TPM, encryption/decryption. Understanding the philosophy behind security solutions helps limit your search for the best controls for your specific security needs. In this chapter, we discuss secure system design principles, security models, the common criteria, and security capabilities of information systems. Domain 3 includes a variety of topics that are discussed in other chapters, including the following. Chapter 1, Security Governance through Principles and Policies. Chapter 6, Cryptography and Symmetric Key Algorithms. Chapter 7, PKI and Cryptographic Applications. Chapter 9, Security Vulnerabilities, Threats and Countermeasures. Chapter 10, Physical Security Requirements. Chapter 14, Controlling and Monitoring Access. Chapter 16, Managing Security Operations. Chapter 21, Malicious Code and Application Attacks. Secure Design Principles. Security should be a consideration at every stage of a system's development. Programmers, developers, engineers, and so on should strive to build security into every application or system they develop, with greater levels of security provided to critical applications and those that process sensitive information. It's extremely important to consider the security implications of a development project in the early stages, because it's much easier to build security into a system during development than it is to add security to an existing system. Developers should research, implement, and manage engineering processes using secure design principles. Note: in addition to the secure design principles of CISSP Objective 3.1, there are other common lists of such principles. These include the U.S. CERT list at us.cisi.gov/bsi/articles/knowledge/principles/design-principles. Objects and subjects. Controlling access to any resource in a secure system involves two entities. The subject is the active entity that makes a request to access a resource. A subject is commonly a user, but it can also be a process, program, computer, or organization. The object is the passive entity that the subject wants to access. An object is commonly a resource, such as a file or printer, but it can also be a user, process, program, computer, or organization. You want to keep a broad understanding of the terms of subject and object rather than only considering users and files. Access is the relationship between a subject and object, which could include reading, writing, changing, deleting, printing, moving, backing up, and many other operations or activities. Keep in mind that the actual entities referenced by the terms subject and object are specific to an individual access request. The entity serving as the object in one access event could serve as the subject in another. For example, Process A may ask for data from Process B. To satisfy Process A's request, Process B must ask for data from Process C. In this example, Table 8.1, Process B is the object of the first request and the subject of the second request. Table 8.1, Subjects and Objects. Request. First request, subject Process A, object Process B. Request. Second request, subject Process B, object Process C. This also serves as an example of transitive trust. Transitive trust is the concept that if A trusts B and B trusts C, then A inherits trust of C through the transitive property, figure 8.1, which works like it would in a mathematical equation. If A equals B and B equals C, then A equals C. In the previous example, when A requests data from B, and then B requests data from C, the data that A receives is essentially from C. Transitive trust is a serious security concern because it may enable bypassing of restrictions or limitations between A and C, especially if A and C both support interaction with B. An example of this would be when an organization blocks access to Facebook or YouTube to increase worker productivity. Thus, workers, A, do not have access to certain internet sites, C. However, if workers are able to have access to a web proxy, virtual private network, VPN, or anonymization service, then this can serve as a means to bypass the local network restriction. In other words, if workers, A, are accessing VPN service B, and the VPN service B can access the blocked internet service C, then A is able to access C through B via a transitive trust exploitation. Closed and open systems. Systems are designed and built according to one of two differing philosophies. A closed system is designed to work well with a narrow range of other systems, generally all from the same manufacturer. The standards for closed systems are often proprietary and not normally disclosed. Open systems, on the other hand, are designed using agreed-upon industry standards. Open systems are much easier to integrate with systems from different manufacturers that support the same standards or that use compatible application programming interfaces, APIs. An API is a defined set of interactions allowed between computing elements, such as applications, services, networking, firmware, and hardware. An API defines the types of requests that can be made, the exact means to make the requests, the data forms of the exchange, and other related requirements, such as authentication and/or session encryption. APIs make interoperability of computing elements possible. Without APIs, computing components would be unable to directly interact and information sharing would not be easy. APIs are what make modern computing and the Internet possible. The app on your smartphone talks to the phone's operating system via an API. The phone's operating system talks over the telco or Wi-Fi network via an API to reach the Cloud Services API in order to submit a request and receive a response. Closed systems are harder to integrate with unlike systems, but this feature could make them more secure. A closed system is often composed of proprietary hardware and software that does not incorporate industry standards or offer an open API. This lack of integration ease means that attacks that typically focus on generic system components either will not work or must be customized to be successful. In many cases, attacking a closed system is harder than launching an attack on an open system, since a unique exploit of a unique vulnerability would be required. In addition to the lack of known vulnerable components on a closed system, it is often necessary to possess more in-depth knowledge of the specific target system to launch a successful attack. Open systems are generally far easier to integrate with other open systems. It is easy, for example, to create a local area network, LAN, with a Microsoft Windows Server machine, a Linux machine, and a Macintosh machine. Although all three computers use different operating systems and could represent up to 3 different hardware architectures, each supports industry standards and open APIs, which makes it easy for network or other communications to occur. This ease of interoperability comes at a price, however. Because standard communications components are incorporated into each of these 3 open systems, there are far more predictable entry points and methods for launching attacks. In general, their openness makes them more vulnerable to attack, and their widespread availability makes it possible for attackers to find plenty of potential targets. Also, open systems are more popular and widely deployed than closed systems, and thus attract more attention from attackers. An attacker who develops basic attacking skills will find more targets that are open systems than closed ones. And arguably, there's a greater body of shared experience and knowledge on how to attack open systems than there is for closed systems. The security of an open system is therefore more dependent on the use of secure and defensive coding practices and a thoughtful defense in-depth deployment strategy. Open source versus closed source. It's also helpful to keep in mind the distinction between open source and closed source systems. An open source solution is one where the source code and other internal logic is exposed to the public. A closed source solution is one where the source code and other internal logic is hidden from the public. Open source solutions often depend on public inspection and review to improve the product over time. Closed source solutions are more dependent on the vendor/programmer to revise the product over time. Both open source and closed source solutions can be available for sale or at no charge, but the term commercial typically implies closed source. However, closed source code is sometimes revealed through either vendor compromise or through decompiling or disassembly. The former is always a breach of ethics and often the law, whereas the latter is a standard element in ethical reverse engineering or systems analysis. It is also the case that a closed source program can be either an open system or a closed system, and an open source program can be either an open system or a closed system. Since these terms are so similar, it is essential to read questions carefully. Additional coverage of open source and other software issues is included in Chapter 20, Software Development Security. Tip: CISSP Objective 3.1 lists 11 secure design principles. 6 of them are covered in this chapter, that is, secure defaults, fail securely, keep it simple, zero trust, privacy by design, and trust but verify. The other 5 are covered in other chapters where they integrate best with broader coverage of similar topics. For threat modeling and defense in depth, see Chapter 1. For least privilege and separation of duties, see Chapter 16. And for shared responsibility, see Chapter 9. Secure defaults. You have probably heard the phrase, the tyranny of the default. But do you really know what this means? Tyranny has several definitions, but the one that applies here is a rigorous condition imposed by some outside agency or force, attributed to American historian Dixon Wechter. Many assume that the settings that are present in a software or hardware product when it is first installed are the optimal settings. This is based on the assumption that the designers and developers of a product know the most about that product, and so the settings they made are likely the best ones. However, this assumption overlooks the fact that often the default settings of a product are selected to minimize installation problems, to avoid increased load on the technical support services. For example, consider the fact that most devices have a default password, which minimizes the costs of support when installing or using the product for the first time. Unfortunately, default settings often make discovery and exploitation of equipment trivial for attackers. Never assume that the default settings of any product are secure. They typically are not, because secure settings would likely get in the way of existing business tasks or system operations. It is always up to the system's administrator and/or company security staff to alter a product's settings to comply with the organization's security policies. Unless your organization hired the developer, that developer did not craft the code or choose settings specifically for your organization's use of their product. A much better assumption is that the default settings of a product are the worst possible options for your organization. Therefore, you need to review each and every setting to determine what it does and what you need it to be configured to do in order to optimize security while supporting business operations. Fortunately, there is some movement toward more secure defaults. As mentioned in Chapter 1, Microsoft's Security Development Lifecycle, SDL, has a motto named SD3+C, which includes the phrase, secure by default. Some products, especially security products, may now be designed with their most secure settings enabled by default. However, such a locked-down product will have fewer enabled capabilities and will likely be less user-friendly. Thus, while being more secure, secure defaults may be an obstacle for those who only want their systems to function. If you are a developer, then it is your responsibility to create detailed explanations of each of the configuration options of your product. You can't assume that customers know everything about your product, especially what the configuration settings are and what each option does to alter its features, operations, communications, and so forth. You may be required to have default settings to make the product as easy to install as possible. But you may be able to provide one or more configurations in either written instructional form or in a file that can be imported or applied. This will go a long way to assist customers with gaining the most advantage from your product while minimizing the security risks. Fail securely. System failures can occur due to a wide range of causes. Once the failure event occurs, how the system or environment handles the failure is important. The most desired result is for an application to fail securely. The first type of failure management is programmatic error handling, aka exception handling. This is the process where a programmer codes in mechanisms to anticipate and defend against errors in order to avoid the termination of execution. Error handling is the inclusion of code that will attempt to handle errors when they arise before they can cause harm or interrupt execution. One such mechanism, which is supported by many languages, is a try-catch statement. This logical block statement is used to place code that could result in an error on the try branch, and then code that will be executed if there is an error on the catch branch. This is similar to if-then-else statements, but it is designed to deftly handle errors. Other mechanisms are to avoid or prevent errors, especially as related to user input. Input sanitization, input filtering, or input validation are some of the terms used to refer to this concept. This often includes checking the input for length, filtering against a block list of unwanted input and escaping meta characters. See more about secure coding practices in Chapter 9, Chapter 15, Security Assessment and Testing, and Chapter 20. There are several similar terms that can be confusing and thus require a bit of focus to comprehend. These terms are fail-soft, fail-secure, fail-safe, fail-open, and fail-closed. Typically, the confusion occurs when not understanding the context where these terms are used. The two primary contexts are the physical world and the digital environment. In the physical world, entities primarily prioritize the protection of people. However, there are some circumstances where assets are protected in priority over people. In the digital world, entities focus on protecting assets, but the type of protection may vary amongst the CIA triad. When a program fails securely, it was able to do so only because it was designed and programmed to. When secure failure is integrated into a system, the designer must make a few difficult choices about what the results of a failure event will be. The first question to be resolved is whether the system can operate in a fail-soft mode. To fail soft is to allow a system to continue to operate after a component fails. This is an alternative to having a failure cause a complete system failure. An example is a typical multitasking operating system that can support numerous simultaneous applications. If one application fails, the others can typically continue to operate. If fail-soft isn't a viable option, then the designer needs to consider the type of product, its deployment scenarios, and the priorities related to failure response. In other words, when the product fails without a fail-soft design, it will fail completely. The designer/developer needs to decide what type of complete failure to perform and what to protect or sacrifice to achieve the planned failure result. There are numerous scenarios to consider. The initial distinction is whether the product is something that affects the physical world, such as a door locking mechanism, or is it primarily a digital asset-focused product, such as a firewall? If a product can affect the physical world, then the life and safety of humans needs to be considered and likely prioritized. This human protection prioritization is called fail-safe. The idea is that when a failure occurs, the system, device, or product will revert to a state that protects the health and safety of people. For example, a fail-safe door will open easily in an emergency in order to allow people to escape a building. But this implies that the protection of assets may be sacrificed in favor of personnel safety. However, in some physical world situations, a product could be designed and intended to protect assets in priority above people, such as a bank vault, medical lab, or even data center. A fail-secure system prioritizes the physical security of assets over any other consideration. For example, a vault door may automatically close and lock when the building enters a state of emergency. This prioritization of asset protection may occur at the potential cost of harming personnel who could be trapped inside. Obviously, the prioritization of physical world products needs to be considered carefully. In the context of the physical world, the terms fail-open is a synonym to fail-safe, and fail-closed is a synonym of fail-secure. If the product is primarily digital, then the focus of security is completely on digital assets. That means the designer must then decide upon the security aspect to prioritize, namely, availability or confidentiality and integrity. If the priority is for maintaining availability, then when the product fails, the connection or communication is allowed to continue. This is known as fail-open. If the priority is for maintaining confidentiality and integrity, then when the product fails, the connection or communication is cut off. This is known as fail-secure, fail closed and or fail safe, again, in the context of a digital environment. Note, the IETF recommends avoiding the use of the term fail-safe when discussing digital-only issues, as it introduces the concept of human safety, which is not a concern in a digital context and thus causes unnecessary confusion. Take note that when the context switches from the physical world to the digital world, the definition of fail-safe changes. An example could be a firewall, which, if designed to fail open, would allow communications without filtering, whereas if implemented, a fail secure, fail closed, or fail safe solution would cut off communications. The fail open state protects availability through the sacrifice of confidentiality and integrity, whereas the fail closed state sacrifices availability in order to protect confidentiality and integrity. Another example of a digital environment event following a fail secure, fail closed, and or fail safe procedure is when an operating system encounters a processing or memory isolation violation. It terminates all executions, then initiates a reboot. This mechanism is known as a stop error, or the blue screen of death, BSOD, in Windows. A condensed summary of the context and protection priority of these terms is presented in Table 8.2. Table 8.2. Failed terms definitions related to physical and digital products. Physical, protect people. State, fail open. Digital, protect availability. Physical, protect people. State, fail safe. Digital, protect confidentiality and integrity. Physical, protect assets. State, fail closed. Digital, protect confidentiality and integrity. Physical, protect assets. State, fail secure. Digital, protect confidentiality and integrity. Keep it simple. Keep it simple is a shortened form of the classic statement of keep it simple, stupid, or keep it stupid simple. This is sometimes called the KISS principle. In the realm of security, this concept is the encouragement to avoid overcomplicating the environment, organization, or product design. The more complex a system, the more difficult it is to secure. The more lines of code, the more challenging it is to thoroughly test it. The more parts there are, the more places there are for things to go wrong. The more features and capabilities, the larger the attack surface. There are many other concepts that have a similar or related emphasis, such as the following. Don't repeat yourself. Dry. The idea of eliminating redundancy in software by not repeating the same code in multiple places, which would increase the difficulty if changes are needed. Computing minimalism. Crafting code so that it uses the least necessary hardware and software resources possible. This is also the goal of the Program Evaluation and Review Technique, PERT, which is discussed in Chapter 20. Rule of least power. Use the least powerful programming language that is suitable for the needed solution. Worse is better, aka New Jersey style. The quality of software does not necessarily increase with an increase in capabilities and functions. There is often a worse software state, that is, fewer functions, which is the better, that is, preferred, maybe more secure, option. You aren't going to need it, Yagni. Programmers should not add capabilities and functions until they are actually necessary. So, rather than create it when you think of it, instead, create it only when you actually need it. It is easy to get caught up in adding complexity to a system, whether that system is a software program or an organizational IT security structure. The KISS principle encourages us all to avoid the overly complex in favor of the streamlined, optimized, and reduced solution. Simpler solutions are easier to secure, easier to troubleshoot, and easier to verify. Zero Trust. Zero Trust is a security concept where nothing inside the organization is automatically trusted. There has long been an assumption that everything on the inside is trusted and everything on the outside is untrusted. This has led to a significant security focus on endpoint devices, the locations where users interact with company resources. An endpoint device could be a user's workstation, a tablet, a smartphone, an Internet of Things IoT device, an industrial control system, ICS, an edge computing sensor, or any public-facing servers in a screened subnet or extranet. The idea that a security perimeter exists between the safe inside and the harmful outside is problematic. There have been too many occurrences of security breaches caused by insiders, as well as external hacker breaches that gained the freedom to perform lateral movement internally once they breached the security barrier. The concept of a security perimeter is further complicated by the use of mobile devices, the cloud, and the proliferation of endpoint devices. For most organizations, there is no longer a clearly defined line between inside and outside. Zero Trust is an alternate approach to security, where nothing is automatically trusted. Instead, each request for activity or access is assumed to be from an unknown and untrusted location until otherwise verified. The concept is never trust, always verify. Since anyone and anything could be malicious, every transaction should be verified before it is allowed to occur. The Zero Trust model is based around assume breach, meaning that you should always assume a security breach has occurred and that whoever or whatever is making a request could be malicious. The goal is to have every access request be authenticated, authorized, and encrypted prior to the access being granted to a resource or asset. The implementation of a Zero Trust architecture does involve a significant shift from historical security management concepts. This shift typically requires internal microsegmentation and strong adherence to the principle of least privilege. This approach prevents lateral movement so that if there is a breach or even a malicious insider, their ability to move about the environment is severely restricted. Tip: microsegmentation is dividing up an internal network into numerous subzones. Each zone is separated from the others by internal segmentation firewalls, ISFWs, subnets, or VLANs. Zones could be as small as a single device, such as a high-value server, or even a client or endpoint device. Any and all communications between zones are filtered, may be required to authenticate, often require session encryption, and may be subjected to allow list and block list control. Zero Trust is implemented using a wide range of security solutions, including internal segmentation firewalls, ISFWs, multi-factor authentication, MFA, identity and access management, IAM, and next-generation endpoint security. A Zero Trust approach to security management can only be successful if a means to continuously validate and monitor user activities is implemented. If a one-time validation mechanism is used, then the opportunity to abuse the system remains, since threats, users, and connection characteristics are always subject to change. Thus, Zero Trust networking can only work if real-time vetting and visibility into user activities is maintained. Tip: in some situations, complete isolation may be needed instead of controlled and filtered interaction. This type of isolation is achieved using an air gap. An air gap is a network security measure employed to ensure that a secure system is physically isolated from other systems. Air gap implies that neither cabled nor wireless network links are available. In order to implement a zero-trust system, an organization must be capable of and willing to abandon some long-held assumptions about security. First and foremost, it must be understood that there is no such thing as a trusted source. No entity, asset, or subject, internal or external, is to be trusted by default. Instead, always assume attackers are already on the inside on every system. From this new, no assumed trust position, it is obvious that traditional default access controls are insufficient. Each and every subject, each and every time, needs to be authenticated, authorized, and encrypted. From there, a continuous real-time monitoring system needs to be established to look for violations and suspicious events. But even with Zero Trust integrated into the IT architecture, it is only an element of a holistic security strategy that is integrated into the entire organization's management processes. Zero Trust has been formalized in NIST SP 800-207 Zero Trust Architecture. Please consult this document to learn more about this revolution in security design. Privacy by Design. Privacy by Design, PBD, is a guideline to integrate privacy protections into products during the early design phase rather than attempting to tack it on at the end of development. It is effectively the same overall concept as security by design or integrated security, where security is to be an element of design and architecture of a product starting at initiation and being maintained throughout the software development lifecycle, SDLC. As described in Ann Cavoukian's paper, Privacy by Design, the 7 foundational principles, implementation and mapping of fair information practices, collections.OLA.org/MON/24005/301946.pdf. The PBD framework is based on 7 foundational principles. Proactive, not reactive. Preventive, not remedial. Privacy as the default. Privacy embedded into design. Full functionality, positive sum, not zero sum. End-to-end security, full lifecycle protection. Visibility and transparency. Respect for user privacy. The goal of PBD is to have developers integrate privacy protections into their solutions in order to avoid privacy violations in the first place. The overall concept focuses on preventions rather than remedies for violations. PBD is also the driving factor behind an initiative to have privacy protections integrated throughout an organization, not just by developers. That business operations and systems design can also integrate privacy protections into their core functions. This, in turn, has led to the Global Privacy Standard, GPS, which was crafted to create a single set of universal and harmonized privacy principles. GPS is to be adopted by countries to use as a guide in developing privacy legislation, used by organizations to integrate privacy protection into their operations, and used by developers to integrate privacy into the products they produce. There is some integration of a few of the principles of PBD in the EU's GDPR. See gdpr-info.eu/issues/privacy-by-design. For more on PBD and GPS, please visit gpsbydesign.org, review the Cavoukian paper mentioned earlier, and read an additional paper, Privacy by Design in Law, Policy and Practice, at collections.OLA.org/MON/25008/312239.pdf. Learn more about privacy in Chapter 4 and about software development security in Chapter 20. Trust but verify. The phrase trust but verify, which is a quote from a Russian proverb, was made famous by former President Ronald Reagan when discussing U.S. relations with the Soviet Union. However, our focus on this phrase is on its use in the security realm. A more traditional security approach of trusting subjects and devices within the company's security perimeter, that is, internal entities, automatically can be called trust but verify. This type of security approach leaves an organization vulnerable to insider attacks and grants intruders the ability to easily perform lateral movement among internal systems. Often, the trust but verify approach depended on an initial authentication process to gain access to the internal secured environment, and then relied on generic access control methods. Due to the rapid growth and changes in the modern threatscape, the trust but verify model of security is no longer sufficient. Most security experts now recommend designing organizational security around the zero trust model. Techniques for ensuring CIA. To ensure the confidentiality, integrity, and availability (CIA) of data, you must ensure that all components that have access to data are secure and well-behaved. Software designers use different techniques to ensure that programs do only what is required and nothing more. Although the concepts we discuss in the following sections all relate to software programs, they are also commonly used in all areas of security. For example, physical confinement guarantees that all physical access to hardware is controlled. Confinement. Software designers use process confinement to restrict the actions of a program. Simply put, process confinement allows a process to read from and write to only certain memory locations and resources. This is also known as sandboxing. It is the application of the principle of least privilege to processes. The goal of confinement is to prevent data leakage to unauthorized programs, users, or systems. The operating system, or some other security component, disallows illegal read/write requests. If a process attempts to initiate an action beyond its granted authority, that action will be denied. In addition, further actions, such as logging the violation attempt, may be taken. Generally, the offending process is terminated. Confinement can be implemented in the operating system itself, such as through process isolation and memory protection, through the use of a confinement application or service, for example, Sandboxie at sandboxie.com, or through a virtualization or hypervisor solution, such as VMware or Oracle's VirtualBox. Bounds. Each process that runs on a system is assigned an authority level. The authority level tells the operating system what the process can do. In simple systems, there may be only two authority levels, user and kernel. The authority level tells the operating system how to set the bounds for a process. The bounds of a process consist of limits set on the memory addresses and resources it can access. The bounds state the area within which a process is confined or contained. In most systems, these bounds segment logical areas of memory for each process to use. It is the responsibility of the operating system to enforce these logical bounds and to disallow access to other processes. More secure systems may require physically bounded processes. Physical bounds require each bounded process to run in an area of memory that is physically separated from other bounded processes, not just logically bounded in the same memory space. Physically bounded memory can be very expensive, but it's also more secure than logical bounds. Bounds can be a means to enforce confinement. Isolation. When a process is confined through enforcing access bounds, that process runs in isolation. Process isolation ensures that any behavior will affect only the memory and resources associated with the isolated process. Isolation is used to protect the operating environment, the kernel of the operating system, and other independent applications. Isolation is an essential component of a stable operating system. Isolation is what prevents an application from accessing the memory or resources of another application, whether for good or ill. Isolation allows for a fail-soft environment so that separate processes can operate normally or fail/crash without interfering or affecting other processes. Isolation is achieved through the enforcement of containment using bounds. Hardware and software isolation implementations are discussed throughout Chapter 9. These three concepts, confinement, bounds, and isolation, make designing secure programs and operating systems more difficult, but they also make it possible to implement more secure systems. Confinement is making sure that an active process can only access specific resources, such as memory. Bounds is the limitation of authorization assigned to a process to limit the resources the process can interact with and the types of interactions allowed. Isolation is the means by which confinement is implemented through the use of bounds. The goals of the concepts is to ensure that the predetermined scope of resource access is not violated, and any failure or compromise of a process has minimal to no effect on any other process. Access controls. To ensure the security of a system, you need to allow subjects to access only authorized objects. Access controls limit the access of a subject to an object. Access rules state which objects are valid for each subject. Further, an object might be valid for one type of access and be invalid for another type of access. There are a wide range of options for access controls, such as discretionary, role-based, and mandatory. Please see Chapter 14 for an in-depth discussion of access controls. Trust and assurance. A trusted system is one in which all protection mechanisms work together to process sensitive data for many types of users, while maintaining a stable and secure computing environment. In other words, trust is the presence of a security mechanism, function, or capability. Assurance is the degree of confidence in satisfaction of security needs. In other words, assurance is how reliable the security mechanisms are at providing security. Assurance must be continually maintained, updated, and re-verified. This is true if the secured system experiences a known change, good or bad, that is, a vendor patch or a malicious exploit, or if a significant amount of time has passed. In either case, change has occurred at some level. Change is often the antithesis of security. It often diminishes security. This is why change management, patch management, and configuration management are so important to security management. Assurance varies from one system to another and often must be established on individual systems. However, there are grades or levels of assurance that can be placed across numerous systems of the same type, systems that support the same services, or systems that are deployed in the same geographic location. Thus, trust can be built into a system by implementing specific security features, whereas assurance is an assessment of the reliability and usability of those security features in a real-world situation. Understand the fundamental concepts of security models. In information security, models provide a way to formalize security policies. Such models can be abstract or intuitive, but all are intended to provide an explicit set of rules that a computer can follow to implement the fundamental security concepts, processes, and procedures of a security policy. A security model provides a way for designers to map abstract statements into a security policy that prescribes the algorithms and data structures necessary to build hardware and software. Thus, a security model gives software designers something against which to measure their design and implementation. Tokens, capabilities, and labels. Several different methods are used to describe the necessary security attributes for an object. A security token is a separate object that is associated with a resource and describes its security attributes. This token can communicate security information about an object prior to requesting access to the actual object. In other implementations, various lists are used to store security information about multiple objects. A capabilities list maintains a row of security attributes for each controlled object. Although not as flexible as the token approach, a capabilities list generally offers quicker lookups when a subject requests access to an object. A third common type of attribute storage is called a security label, which is generally a permanent part of the object to which it's attached. Once a security label is set, it usually cannot be altered. This permanence provides another safeguard against tampering that neither tokens nor capabilities lists provide. You'll explore several security models in the following sections. All of them can shed light on how security enters into computer architectures and operating system design. Trusted Computing Base, State Machine Model, Information Flow Model, Non-Interference Model, Take-Grant Model, Access Control Matrix, Bell-LaPadula Model, BIBA Model, Clark-Wilson Model, Brewer and Nash Model, Gauguin-Messeguer Model, Sutherland Model, Graham-Denning Model, Harrison-Russo-Ullman Model. Case Study. There are several more security models you might learn about if you formally study computer security, systems design, or application development. Some of those include the Object Capability Model, Lipner's Model, the Boebert and Kane Integrity Model, the Two-Compartment Exchange Karger Model, Gong's JDK Security Model, the Lee-Shockley Model, the Juniman Model, and more. However, the ones we have expanded on in this chapter should be more than sufficient for your CISSP exam prep. Trusted Computing Base. The Trusted Computing Base TCB design principle is the combination of hardware, software, and controls that work together to form a trusted base to enforce your security policy. The TCB is a subset of a complete information system. It should be as small as possible so that a detailed analysis can reasonably ensure that the system meets design specifications and requirements. The TCB is the only portion of that system that can be trusted to adhere to and enforce the security policy. It is the responsibility of TCB components to ensure that a system behaves properly in all cases and that it adheres to the security policy under all circumstances. Security perimeter. The security perimeter of your system is an imaginary boundary that separates the TCB from the rest of the system. Figure 8.2. This boundary ensures that no insecure communications or interactions occur between the TCB and the remaining elements of the computer system. For the TCB to communicate with the rest of the system, it must create secure channels, also called trusted paths. A trusted path is a channel established with strict standards to allow necessary communication to occur without exposing the TCB to security exploitations. A security perimeter may also allow for the use of a trusted shell. A trusted shell allows a subject to perform command line operations without risk to the TCB or the subject. A trusted shell prevents the subject from being able to break out of isolation to affect the TCB, and in turn prevents other processes from breaking into the shell to affect the subject. reference monitors, and kernels. The part of the TCB that validates access to every resource prior to granting access requests is called the reference monitor, Figure 8.2. The reference monitor stands between every subject and object, verifying that a requesting subject's credentials meet the object's access requirements before any requests are allowed to proceed. Effectively, the reference monitor is the access control enforcer for the TCB. The reference monitor enforces access control or authorization based on the desired security model, whether discretionary, mandatory, role-based, or some other form of access control. The collection of components in the TCB that work together to implement reference monitor functions is called the security kernel. The reference monitor is a concept or theory that is put into practice via the implementation of a security kernel in software and hardware. The purpose of the security kernel is to launch appropriate components to enforce reference monitor functionality and resist all known attacks. The security kernel mediates all resource access requests, granting only those requests that match the appropriate access rules in use for a system. State-machine model. The state-machine model describes a system that is always secure no matter what state it is in. It is based on the computer science definition of a finite state machine, FSM. An FSM combines an external input with an internal machine state to model all kinds of complex systems, including parsers, decoders, and interpreters. Given an input and a state, an FSM transitions to another state and may create an output. Mathematically, the next state is a function of the current state and the input next state. That is, the next state equals F, open parentheses, input, current state, close parentheses. Likewise, the output is also a function of the input and the current state output. That is, the output equals F, open parentheses, input, current state, close parentheses. According to the state-machine model, a state is a snapshot of a system at a specific moment in time. If all aspects of a state meet the requirements of the security policy, that state is considered secure. A transition occurs when accepting input or producing output. A transition always results in a new state, also called a state transition. All state transitions must be evaluated. If each possible state transition results in another secure state, the system can be called a secure state machine. A secure state machine model system always boots into a secure state, maintains a secure state across all transitions, and allows subjects to access resources only in a secure manner compliant with the security policy. The secure state machine model is the basis for many other security models. Information flow model. The information flow model focuses on controlling the flow of information. Information flow models are based on the state machine model. Information flow models don't necessarily deal with only the direction of information flow. They can also address the type of flow. Information flow models are designed to prevent unauthorized, insecure, or restricted information flow, often between different levels of security known as multi-level models. Information flow can be between subjects and objects at the same time or different classification levels. An information flow model allows all authorized information flows and prevents all unauthorized information flows. Another interesting perspective on the information flow model is that it is used to establish a relationship between two versions or states of the same object when those two versions or states exist at different points in time. Thus, information flow dictates the transformation of an object from one state at one point in time to another state at another point in time. The information flow model also addresses covert channels by specifically excluding all undefined flow pathways. Non-interference model. The non-interference model is loosely based on the information flow model. However, instead of being concerned about the flow of information, the non-interference model is concerned with how the actions of a subject at a higher security level affect the system state or the actions of a subject at a lower security level. Basically, the actions of subject A, high, should not affect or interfere with the actions of subject B, low, or even be noticed by subject B. If such violations occur, subject B may be placed into an insecure state or be able to deduce or infer information about a higher level of classification. This is a type of information leakage and implicitly creates a covert channel. Thus, the non-interference model can be imposed to provide a form of protection against damage caused by malicious programs, such as Trojan horses, backdoors, and rootkits. Real-world scenario. Composition theories. Some other models that fall into the information flow category build on the notion of inputs and outputs between multiple systems. These are called composition theories because they explain how outputs from one system relate to inputs to another system. There are three composition theories. Cascading. Input for one system comes from the output of another system. Feedback. One system provides input to another system, which reciprocates by reversing those roles so that System A first provides input for System B, and then System B provides input to System A. Hookup. One system sends input to another system, but also sends input to external entities. Take-grant model. The take-grant model employs a directed graph, figure 8.3, to dictate how rights can be passed from one subject to another or from a subject to an object. Simply put, a subject, X, with the grant right can grant another subject, Y, or another object, Z, any right that subject, X, possesses. Likewise, a subject, X, with the take right can take a right from another subject, Y. In addition to these two primary rules, the take-grant model has a create rule and a remove rule to generate or delete rights. The key to this model is that using these rules allows you to figure out when rights in the system can change and where leakage, that is, unintentional distribution of permissions, can occur. In essence, here are the four rules of the take-grant model. Take rule allows a subject to take rights over an object. Grant rule allows a subject to grant rights to an object. Create rule allows a subject to create new rights. Remove rule allows a subject to remove rights it has. It is interesting to ponder that the take and grant rules are effectively a copy function. This can be recognized in modern OSs in the process of inheritance, such as subjects inheriting a permission from a group or a file inheriting ACL values from a parent folder. The two additional rules, create and remove, which are not defined by a directed graph, are also commonly present in modern operating systems. For example, to obtain permission on an object, that permission does not have to be copied from a user account that already has that permission. Instead, it is simply created by an account with privileged capability of create or assign permissions, which can be the owner of an object or a subject with full control or administrative privileges over the object. Access control matrix. An access control matrix is a table of subjects and objects that indicates the actions or functions that each subject can perform on each object. Each column of the matrix is an access control list, ACL, pulled from objects. Once sorted, each row of the matrix is a capabilities list for each listed subject. An ACL is tied to an object. It lists the valid actions each subject can perform. A capability list is tied to the subject. It lists valid actions that can be taken on each object included in the matrix. From an administrative perspective, using only capability lists for access control is a management nightmare. A capability list method of access control can be accomplished by storing on each subject a list of rights the subject has for every object. This effectively gives each user a key ring of accesses and rights to objects within the security domain. To remove access to a particular object, every user, subject, that has access to it must be individually manipulated. Thus, managing access on each user account is much more difficult than managing access on each object. In other words, via ACLs. A capabilities table can be created by pivoting an access control matrix. This results in the columns being subjects and the rows being ACLs from objects. The access control matrix shown in Table 8.3 is for a discretionary access control system. A mandatory or role-based matrix can be constructed simply by replacing the subject names with classifications or roles. Access control matrices are used by systems to quickly determine whether the requested action by a subject for an object is authorized. Table 8.3. An access control matrix. Subject, Bob. Document file, read. Printer, no access. Network folder share, no access. Subject, Mary. Document file, no access. Printer, no access. Network folder share, read. Subject, Amanda. Document file, read, write. Printer, print. Network folder share, no access. Subject, Mark. Document file, read, write. Printer, print. Network folder share, read, write. Subject, Catherine. Document file, read, write. Printer, print, manage print queue. Network folder share, read, write, execute. Subject, Colin. Document file, read, write, change permissions. Printer, print, manage print queue, change permissions. Network folder share, read, write, execute, change permissions. Bell-LaPadula model. The U.S. Department of Defense, DoD, developed the Bell-LaPadula model in the 1970s based on the DoD's multi-level security policies. The multi-level security policy states that a subject with any level of clearance can access resources at or below its clearance level. However, within clearance levels, access to compartmentalized objects is granted only on a need-to-know basis. By design, the Bell-LaPadula model presents the leaking or transfer of classified information to less secure clearance levels. This is accomplished by blocking lower classified subjects from accessing higher classified objects. With these restrictions, the Bell-LaPadula model is focused on maintaining confidentiality and does not address any other aspects of object security. Case study. Lattice-based access control. This general category for non-discretionary access controls is covered in Chapter 13, Managing Identity and Authentication. Here's a quick preview on that more detailed coverage of this subject, which drives the underpinnings for most access control security models. Subjects under lattice-based access controls are assigned positions in a lattice, that is, a multi-layered security structure or multi-leveled security domains. Subjects can access only those objects that fall into the range between the least upper bound, LUB, the nearest security label or classification higher than their lattice position, and the greatest, that is highest, lower bound, GLB. the nearest security label or classification lower than their lattice position of the labels or classifications for their lattice position. This model is built on a state machine concept and the information flow model. It also employs mandatory access controls and is a lattice-based access control concept. The lattice tiers are the classification levels defined by the security policy of the organization. There are three basic properties of this state machine. The simple security property states that a subject may not read information at a higher sensitivity level, no read-up. The star security property states that a subject may not write information to an object at a lower sensitivity level, no write-down. This is also known as the confinement property. The discretionary security property states that the system uses an access matrix to enforce discretionary access control. These first two properties define the states into which the system can transition. No other transitions are allowed. All states accessible through these two rules are secure states. Thus, Bell-LaPadula modeled systems offer state machine model security. The Bell-LaPadula properties are in place to protect data confidentiality. A subject cannot read an object that is classified at a higher level than the subject is cleared for. Because objects at one level have data that is more sensitive or secret than data in objects at a lower level, a subject who is not a trusted subject cannot write data from one level to an object at a lower level. That action would be similar to pasting a top-secret memo into an unclassified document file. The third property enforces a subject's job/role-based need to know in order to access an object. Note: an exception in the Bell-LaPadula model states that a trusted subject is not constrained by the star security property. A trusted subject is defined as a subject that is guaranteed not to consummate a security breaching information transfer, even if it is possible. This means that a trusted subject is allowed to violate the star security property and perform a write-down, which is necessary when performing valid object declassification or reclassification. The Bell-LaPadula model was designed in the 1970s, so it does not support many operations that are common today, such as file sharing and networking. It also assumes secure transitions between security layers and does not address covert channels. BIBA model. The BIBA model was designed after the Bell-LaPadula model, but it focuses on integrity. The BIBA model is also built on a state machine concept, is based on information flow, and is a multi-level model. In fact, the BIBA model is the inverted Bell-LaPadula model. The properties of the BIBA model are as follows. The simple integrity property states that a subject cannot read an object at a lower integrity level, no read down. The star integrity property states that a subject cannot modify an object at a higher integrity level, no write up. Note: in both the BIBA and Bell-LaPadula models, there are two properties that are inverses of each other, simple and star. However, they may also be labeled as axioms, principles, or rules. What you should focus on is the simple and star designations. Take note that simple is always about reading and star is always about writing. In both cases, the rules define what cannot or should not be done. Usually, what is not prevented or blocked is allowed. Thus, even though a rule is stated as a no declaration, its opposite direction is implied as allowed. On the exam, the first and best answer as to the definition or meaning of a property is the negative statement. But if that is not an option, then the opposite implied operation is the next best selection. Figure 8.5, which can be found in the print version of the book, illustrates these BIBA model properties. Consider the BIBA properties. The second property of the Biba model is pretty straightforward. A subject cannot write to an object at a higher integrity level. That makes sense. What about the first property? Why can't a subject read an object at a lower integrity level? The answer takes a little thought. Think of integrity levels as being like the purity level of air. You would not want to pump air from the smoking section into the clean room environment. The same applies to data. When integrity is important, you do not want unvalidated data read into validated documents. The potential for data contamination is too great to permit such access. Biba was designed to address three integrity issues. Prevent modification of objects by unauthorized subjects. Prevent unauthorized modification of objects by authorized subjects. Protect internal and external object consistency. Biba requires that all subjects and objects have a classification label. It is still a DoD-derived security model. Thus, data integrity protection is dependent on data classification. Critiques of the Biba model revealed a few drawbacks. It addresses only integrity, not confidentiality or availability. It focuses on protecting objects from external threats. It assumes that internal threats are handled programmatically. It does not address access control management, and it doesn't provide a way to assign or change an object's or subject's classification level. It does not prevent covert channels. Memorizing the properties of Bell, LaPadula, and Biba can be challenging, but there is a shortcut. If you can memorize the graphical layout in Figure 8.6 above the dotted line, then you can figure out the rest. Notice that Bell LaPadula is placed on the left and Biba is on the right, and the security benefit of each is listed below the model name. Then, only the Bell LaPadula model's simple property is listed. That property is no read up, which is represented by an arrow pointing upward that is crossed out and labeled by an S for simple and an R for read. From there, all of the other rules are the opposing element of the pair or inverted. By memorizing the top graphic, once you are in the exam, you can draw that out on the provided dry erase board. Then you can quickly create the other rules. First, under Bell LaPadula, draw an arrow pointing down, cross it out, then label it with an asterisk for star and a W for right. Now you have the no write down star property. You can then draw dotted arrows in the opposite direction of these two to indicate the implied opposite direction is allowed. Then take these four arrows of Bell LaPadula and completely flip them over top to bottom to create the rules for Biba. The result should be the bottom graphic below the dotted line. Clark-Wilson model. The Clark-Wilson model uses a multifaceted approach to enforcing data integrity. Instead of defining a formal state machine, the Clark-Wilson model defines each data item and allows modifications through only a limited or controlled intermediary program or interface. The Clark-Wilson model does not require the use of a lattice structure. Rather, it uses a three-part relationship of subject/program/object, or subject/transaction/object, known as a triple or an access control triplet. Subjects do not have direct access to objects. Objects can be accessed only through programs. Through the use of two principles, well-formed transactions and separation of duties, the Clark-Wilson model provides an effective means to protect integrity. Well-formed transactions take the form of programs. A subject is able to access objects only by using a program, interface, or access portal. Figure 8.7. Each program has specific limitations on what it can and cannot do to an object, such as a database or other resource. This effectively limits the subject's capabilities. This is known as a constrained, limiting, or restrictive interface. If the programs are properly designed, then the triple relationship provides a means to protect the integrity of the object. Clark-Wilson defines the following items and procedures. A constrained data item, CDI, is any data item whose integrity is protected by the security model. An unconstrained data item, UDI, is any data item that is not controlled by the security model. Any data that is to be input and hasn't been validated, or any output, would be considered an unconstrained data item. An integrity verification procedure, IVP, is a procedure that scans data items and confirms their integrity. Transformation procedures, TPs, are the only procedures that are allowed to modify a CDI. The limited access to CDIs through TPs forms the backbone of the Clark-Wilson integrity model. The Clark-Wilson model uses security labels to grant access to objects, but only through transformation procedures and a restricted interface model. A restricted interface model uses classification-based restrictions to offer only subject-specific authorized information and functions. One subject at one classification level will see one set of data and have access to one set of functions, whereas another subject at a different classification level will see a different set of data and have access to a different set of functions. The different functions made available to different levels or classes of users may be implemented by either showing all functions to all users, but disabling those that are not authorized for a specific user, or by showing only those functions granted to a specific user. Through these mechanisms, the Clark-Wilson model ensures that data is protected from unauthorized changes from any user. In effect, the Clark-Wilson model enforces separation of duties. The Clark-Wilson design makes it a common model for commercial applications. Tip: the Clark-Wilson model was designed to protect integrity using the access control triplet. However, though the intermediary interface can be programmed to limit what can be done to an object by a subject, it can just as easily be programmed to limit or restrict what objects are shown to a subject. Thus, this concept can lend itself readily to protect confidentiality. In many situations, there is an intermediary program between a subject and an object. If the focus of that intermediary is to protect integrity, then it is an implementation of the Clark-Wilson model. If it is intended to protect confidentiality, then they are benefiting from an alternate use of the intermediary program. Use of the access control triplet to protect confidentiality does not seem to have its own model name. Brewer and Nash model. The Brewer and Nash model was created to permit access controls to change dynamically based on a user's previous activity, making it a kind of state machine model as well. This model applies to a single integrated database. It seeks to create security domains that are sensitive to the notion of conflict of interest. For example, someone who works at Company C who has access to proprietary data for Company A should not also be allowed access to similar data for Company B if those two companies compete with each other. This model creates a class of data that defines which security domains are potentially in conflict and prevents any subject with access to one domain that belongs to a specific conflict class from accessing any other domain that belongs to the same conflict class. Metaphorically, this puts a wall around all other information in any conflict class. Thus, this model also uses the principle of data isolation within each conflict class to keep users out of potential conflict of interest situations. For example, management of company datasets. Because company relationships change all the time, dynamic updates to members of and definitions for conflict classes are important. Another way of looking at or thinking of the Brewer and Nash model is of an administrator having full control access to a wide range of data in a system based on their assigned job responsibilities and work tasks. However, at the moment an action is taken against any data item, the administrator's access to any conflicting data items is temporarily blocked. Only data items that relate to the initial data item can be accessed during the operation. Once the task is completed, the administrator's access returns to full control. Brewer and Nash was sometimes known as the Chinese wall model, but this term is deprecated. Instead, other terms of ethical wall and cone of silence have been used to describe Brewer and Nash. Gauguin-Messeguer model. The Gauguin-Messeguer model is an integrity model, although not as well known as Biba and the others. In fact, this model is said to be the foundation of non-interference conceptual theories. Often, when someone refers to a non-interference model, they are actually referring to the Gauguin-Messeguer model. The Gauguin-Messeguer model is based on predetermining the set or domain that is a list of objects that a subject can access. This model is based on automation theory and domain separation. This means subjects are allowed only to perform predetermined actions against predetermined objects. When similar users are grouped into their own domain, that is, collective, the members of one subject domain cannot interfere with the members of another subject domain. Thus, subjects are unable to interfere with each other's activities. Sutherland model. The Sutherland model is an integrity model. It focuses on preventing interference in support of integrity. It is formally based on the state-machine model and the information flow model. However, it does not directly indicate specific mechanisms for protection of integrity. Instead, the model is based on the idea of defining a set of system states, initial states, and state transitions. Through the use of only these predetermined secure states, integrity is maintained and interference is prohibited. A common example of the Sutherland model is its use to prevent a covert channel from being used to influence the outcome of a process or activity. Graham-Denning model. The Graham-Denning model is focused on the secure creation and deletion of both subjects and objects. Graham-Denning is a collection of 8 primary protection rules or actions that define the boundaries of certain secure actions. Securely create an object, securely create a subject, securely delete an object, securely delete a subject, securely provide the read access right, securely provide the grant access right, securely provide the delete access right, securely provide the transfer access right. Usually, the specific abilities or permissions of a subject over a set of objects is defined in an access matrix, aka access control matrix. Harrison-Russo-Ullman model. The Harrison-Russo-Ullman HRU model focuses on the assignment of object access rights to subjects, as well as the resilience of those assigned rights. It is an extension of the Graham-Denning model. It is centered around the establishment of a finite set of procedures or access rights that can be used to edit or alter the access rights of a subject over an object. The state of access rights under HRU can be expressed in a matrix, where the rows are subjects and the columns are objects, which will include the subjects because they can be objects as well. The intersection of each row and column will include the specific procedures that each subject is allowed to perform against each object. Additionally, a finite set of commands or primitives is defined that controls how the matrix can be modified by authorized subjects. These primitives include adding or removing access rights, subjects, and/or objects from the matrix. There are also integrity rules, such as In order to create or add a subject or object to the matrix, it must not already exist. In order to remove a subject or object from the matrix, it must already exist. And if several commands are performed at once, they must all operate successfully, or none of the commands will be applied. Disambiguating the word star in models. The term star presents a few challenges when it comes to security models. For one thing, there is no formal security model named star model. However, both the Bell-LaPadula and the BIBA models have a star property, which is discussed in their respective sections in this chapter. Although not a model, the Cloud Security Alliance, CSA, also has a star program. CSA's Security Trust Assurance and Risk STAR program focuses on improving cloud service provider, CSP security, through auditing, transparency, and integration of standards. Although not related to security, there is also Galbraith's STAR model, which helps businesses organize divisions and departments to achieve business missions and goals and adjust over time for long-term viability. This model is based around 5 main areas of business administration that need to be managed, balanced, and harnessed toward the mission and goals of the organization. The 5 areas of Galbraith's STAR model are strategy, structure, processes, rewards, and people. Understanding how STAR is used in the context of the Bell-LaPadula and BIBA models, CSA's STAR program, and Galbraith's STAR model will help you distinguish what is meant when you see the word used in different contexts. Select controls based on systems security requirements. Those who purchase information systems for certain kinds of applications, for example, national security agencies, whose sensitive information may be extremely valuable or dangerous in the wrong hands, or central banks or security traders that have certain data that may be worth billions of dollars, often want to understand the security strengths and weaknesses of systems prior to acquisition. Such buyers are often willing to consider only systems that have been subjected to formal evaluation processes in advance and have received some kind of security rating. Often trusted third parties are used to perform security evaluations. The most important result from such testing is their seal of approval that the system meets all essential criteria. Common criteria. The Common Criteria, CC, defines various levels of testing and confirmation of systems security capabilities, and the number of the level indicates what kind of testing and confirmation has been performed. Nevertheless, it's wise to observe that even the highest CC ratings do not equate to a guarantee that such systems are completely secure or that they are entirely devoid of vulnerabilities or susceptibilities to exploit. The Common Criteria was designed as a dynamic, subjective product evaluation model and replaced previous static systems, such as the U.S. Department of Defense's Trusted Computer System Evaluation Criteria, TSEC, and the EU's Information Technology Security Evaluation Criteria, ITSEC. A document titled Arrangement on the Recognition of Common Criteria Certificates in the Field of IT Security was signed by representatives from government organizations in Canada, France, Germany, the United Kingdom, and the United States in 1998, making the document an international standard. Since then, 23 additional countries have signed the arrangement. The original arrangement documentation has been formally adopted as a standard and published as ISO/IEC 15408-1, -2, and -3, and primarily labeled as Information Technology, Security Techniques, Evaluation Criteria for IT Security. Note: there is a revision of ISO/IEC 15408 currently underway, as of fall 2020. It was labeled as ISO/IED 15408-1, -2 or -3 2020, which may be published by the time this book is published. The latest versions of ISO/IEC standards are available at standards.iso.org/ITTF/publicly available standards/index.html. The objectives of the CC guidelines are as follows: to add to buyers' confidence in the security of evaluated, rated IT products, to eliminate duplicate evaluations. Among other things, this means that if one country, agency, or validation organization follows the CC in rating specific systems and configurations, others elsewhere need not repeat this work. To keep making security evaluations more cost-effective and efficient, to make sure evaluations of IT products adhere to high and consistent standards, to promote evaluation and increase availability of evaluated rated IT products, to evaluate the functionality, in other words, what the system does, and assurance, in other words, how much can you trust the system, of the target of evaluation, TOE. The common criteria process is based on two key elements: protection profiles and security targets. Protection profiles, PPs, specify for a product that it is to be evaluated, the TOE, the security requirements and protections, which are considered the security desires or the I want from a customer. Security targets, STs, specify the claims of security from the vendor that are built into a TOE. STs are considered the implemented security measures or the I will provide from the vendor. In addition to offering security targets, vendors may offer packages of additional security features. A package is an intermediate grouping of security requirement components that can be added to or removed from a TOE, like the option packages when purchasing a new vehicle. This system of the PP and ST allows for flexibility, subjectivity, and customization of an organization's specific security functional and assurance requirements over time. An organization's PP is compared to various STs from the selected vendor's TOEs. The closest or best match is what the client purchases. The client initially selects a vendor based on published or marketed evaluation assurance levels, EALs, for currently available systems. Using common criteria to choose a vendor allows clients to request exactly what they need for security rather than having to use static, fixed security levels. It also allows vendors more flexibility on what they design and create. A well-defined set of common criteria supports subjectivity and versatility, and it automatically adapts to changing technology and threat conditions. Furthermore, the EALs provide a method for comparing vendor systems that is more standardized, like the old TSEC. Table 8.4 summarizes EALs 1 through 7. For a complete description of EALs, consult the CC standard documents. Table 8.4 Common Criteria Evaluation Assurance Levels. Level EAL1. Assurance level, functionally tested, description. Applies when some confidence in correct operation is required, but where threats to security are not serious. This is of value when independent assurance that due care has been exercised in protecting personal information is necessary. Level EAL2. Assurance level, structurally tested, description. Applies when delivery of design information and test results are in keeping with good commercial practices. This is of value when developers or users require low to moderate levels of independently assured security. It is especially relevant when evaluating legacy systems. Level EAL3. Assurance level, methodically tested and checked, description. applies when security engineering begins at the design stage and is carried through without substantial subsequent alteration. This is of value when developers or users require a moderate level of independently assured security, including thorough investigation of TOE and its development. Level EAL4. Assurance level. Methodically designed, tested, and reviewed. Description. Applies when rigorous, positive security engineering and good commercial development practices are used. This does not require substantial specialist knowledge, skills, or resources. It involves independent testing of all TOE security functions. Level EAL5. Assurance level, semi-formally designed and tested. Description. Uses rigorous security engineering and commercial development practices, including specialist security engineering techniques for semi-formal testing. This applies when developers or users require a high level of independently assured security in a planned development approach, followed by rigorous development. Level EAL6. Assurance level, semi-formally verified, designed, and tested. Description. Uses direct, rigorous security engineering techniques at all phases of design, development, and testing to produce a premium TOE. This applies when TOEs for high-risk situations are needed, where the value of protected assets justifies additional costs. Extensive testing reduces risks of penetration, probability of covert channels, and vulnerability to attack. Level EAL7. Assurance level, formally verified, designed, and tested. Description. Used only for highest risk situations or where high-value assets are involved. This is limited to TOEs where tightly focused security functionality is subject to extensive formal analysis and testing. Though the CC guidelines are flexible and accommodating enough to capture most security needs and requirements, they are by no means perfect. As with other evaluation criteria, the CC guidelines do nothing to make sure that how users act on data is also secure. The CC guidelines also do not address administrative issues outside the specific purview of security. As with other evaluation criteria, the CC guidelines do not include evaluation of security in situ. That is, they do not address controls related to personnel, organizational practices and procedures, or physical security. Likewise, controls over electromagnetic emissions are not addressed, nor are the criteria for rating the strength of cryptographic algorithms explicitly laid out. Nevertheless, the CC guidelines represent some of the best techniques whereby systems may be rated for security. Common criteria documentation is available at commoncriteriaportal.org/CCRA. Visit this site to get information on the current version of the CC guidelines and guidance on using the CC, along with lots of other useful, relevant information. Tip. International Organization for Standardization, ISO, is a worldwide standards-setting group of representatives from various national standards organizations. ISO defines standards for industrial and commercial equipment, software, protocols, and management, among others. It issues 6 main products: international standards, technical reports, technical specifications, publicly available specifications, technical corrigenda, and guides. ISO standards are widely accepted across many industries and have even been adopted as requirements or laws by various governments. For more information on ISO, please visit the website at iso.org. Authorization to operate. For many environments, it is necessary to obtain an official approval to use secured equipment for operational objectives. This is often referred to as an authorization to operate, ATO. ATO is the current term for this concept as defined by the Risk Management Framework, RMF, which replaces the previous term of accreditation. An ATO is an official authorization to use a specific collection of secured IT/IS systems to perform business tasks and accept the identified risk. The assessment and assignment of an ATO is performed by an authorizing official, AO. An AO is an authorized entity who can evaluate an IT/IS system, its operations, and its risks, and potentially issue an ATO. Other terms for AO include Designated Approving Authority, DAA, Approving Authority, AA, Security Control Assessor, SCA, and Recommending Official, RO. Note: NIST maintains an excellent glossary with references at csrc.nist.gov/glossary. A typical ATO is issued for 5 years. Although assigned timeframes vary, and the AO can adjust the timeframe even after issuing an ATO, and must be reobtained whenever one of the following conditions occurs. The ATO timeframe has expired, the system experiences a significant security breach, the system experiences a significant security change. The AO has the discretion to determine which breaches or security changes result in a loss of ATO, either a modest intrusion event or the application of a substantial security patch could cause the negation of an ATO. An AO can issue 4 types of authorization decisions. Authorization to operate. This decision is issued when risk is managed to an acceptable level. Common control authorization. This decision is issued when a security control is inherited from another provider, and when the risk associated with the common control is at an acceptable level and already has an ATO from the same AO. Authorization to use. This decision is issued when a third-party provider, such as a cloud service, provides IT/IS servers that are deemed to have risk at an acceptable level. It is also used to allow for reciprocity in accepting another AO's ATO. Denial of authorization. This decision is issued when risk is unacceptable. Please see NIST SP 837-R2 for more on the Risk Management Framework and authorization. Tip: the RMF ATO concept replaces the previous Certification and Accreditation C&A process. There are a few remaining references to C&A in NIST documents, but they are mostly from older publications or are marked as CFD, which stands for Candidates for Deletion. Understand security capabilities of information systems. The security capabilities of information systems include memory protection, virtualization, Trusted Platform Module, TPM, encryption/decryption, interfaces, and fault tolerance. It is important to carefully assess each aspect of the infrastructure to ensure that it sufficiently supports security. Without an understanding of the security capabilities of information systems, it is impossible to evaluate them, nor is it possible to implement them properly. Memory protection. Memory protection is a core security component that must be designed and implemented into an operating system. It must be enforced regardless of the programs executing in the system. Otherwise, instability, violation of integrity, denial of service, and disclosure are likely results. Memory protection is used to prevent an active process from interacting with an area of memory that was not specifically assigned or allocated to it. Memory protection is discussed throughout Chapter 9 in relation to the topics of isolation, virtual memory, segmentation, memory management and protection rings, as well as protections against buffer, that is memory, overflows. Meltdown and Spectre. In late 2017, two significant memory errors were discovered. These issues were given the names Meltdown and Spectre. These problems arise from the methods used by modern CPUs to predict future instructions to optimize performance. This can enable the processor to seemingly make reliable predictions about what code to retrieve or process even before requested. However, when the speculative execution is wrong, the procedure is not completely reversed. That is, not every incorrect predicted step is undone. This can result in some data remnants being left behind in memory in an unprotected state. Meltdown is an exploitation that can allow for the reading of private kernel memory contents by a non-privileged process. Spectre can enable the wholesale theft of memory contents from other running applications. An astoundingly wide range of processors are vulnerable to one or both of these exploits. Although two different issues, they were discovered nearly concurrently and made public at the same time. Patches are widely available to address these issues in existing hardware, and future processors should have native mechanisms to prevent such exploitations. But such patches often cause a reduction in performance, so application of the patch should be considered carefully. For a thorough discussion of these concerns, please listen to the Security Now podcast or read the show notes of episodes number 645, The Speculation Meltdown, number 646, In Spectre, number 648, Post-Spectre, and number 662, Spectre Next Gen, at grc.com/securitynow.htm. Virtualization. Virtualization technology is used to host one or more operating systems within the memory of a single host computer, or to run applications that are not compatible with the host OS. Virtualization can be a tool to isolate OSs, test suspicious software, or implement other security protections. See Chapter 9 for more information about virtualization. Trusted Platform Module. The Trusted Platform Module, TPM, is both a specification for a crypto processor chip on a main board and the general name for implementation of the specification. A TPM can be used to implement a broad range of cryptography-based security protection mechanisms. A TPM chip is often used to store and process cryptographic keys for a hardware-supported or OS-implemented local storage device encryption system. A TPM is an example of a hardware security module, HSM. An HSM is a crypto processor used to manage and store digital encryption keys, accelerate crypto operations, support faster digital signatures, and improve authentication. An HSM can be a chip on a motherboard, an external peripheral, a network-attached device, or an extension card, which is inserted into a device, such as a router, firewall, or rack-mounted server blade. HSMs include tamper protection to prevent their misuse, even if an attacker gains physical access. Interfaces. A constrained or restricted interface is implemented within an application to restrict what users can do or see based on their privileges. Users with full privileges have access to all the capabilities of the application. Users with restricted privileges have limited access. Applications constrain the interface using different methods. A common method is to hide the capability if the user doesn't have permissions to use it. Commands might be available to administrators via a menu or by right-clicking an item. But If a regular user doesn't have permissions, the command does not appear. Other times, the command is shown but is dimmed or disabled. The regular user can see it, but will not be able to use it. The purpose of a constrained interface is to limit or restrict the actions of both authorized and unauthorized users. The use of such an interface is a practical implementation of the Clark-Wilson model of security. Fault tolerance. Fault tolerance is the ability of a system to suffer a fault but continue to operate. Fault tolerance is achieved by adding redundant components, such as additional disks within a redundant array of inexpensive disks, RAID array, or additional servers within a failover clustered configuration. Fault tolerance is an essential element of security design. It is also considered part of avoiding single points of failure and the implementation of redundancy. For more details on fault tolerance, redundant servers, RAID, and failover solutions, see Chapter 18, Disaster Recovery Planning. Encryption/decryption. Encryption is the process of converting plain text to ciphertext, whereas decryption reverses that process. Symmetric and asymmetric methods of encryption and decryption can be used to support a wide range of security solutions to protect confidentiality and integrity. Please see the full coverage of cryptography in Chapters 6 and 7. Summary. Secure systems are not just assembled. They are designed to support security. Systems that must be secure are judged for their ability to support and enforce the security policy. Programmers should strive to build security into every application they develop, with greater levels of security provided to critical applications and those that process sensitive information. There are numerous issues related to the establishment and integration of security into a product, including managing subjects and objects and their relationships, using open or closed systems, managing secure defaults, designing a system to fail securely, abiding by the Keep It Simple postulate, implementing zero trust instead of trust but verify, and incorporating privacy by design. CIA can be protected using confinement, bounds, and isolation. Controls are used to implement security protections. Proper security concepts, controls, and mechanisms must be integrated before and during the design and architectural period in order to produce a reliably secure product. A trusted system is one in which all protection mechanisms work together to process sensitive data for many types of users, while maintaining a stable and secure computing environment. In other words, trust is the presence of a security mechanism or capability. Assurance is the degree of confidence in satisfaction of security needs. In other words, assurance is how reliable the security mechanisms are at providing security. When security systems are designed, it is often helpful to derive security mechanisms from standard security models. Some of the security models that should be recognized include the Trusted Computing Base, State Machine Model, Information Flow Model, Non-Interference Model, Take-Grant Model, Access Control Matrix, Bell-LaPadula Model, BIBA Model, Clark-Wilson Model, Brewer and Nash Model, Gauguin-Messeguer Model, Sutherland Model, Graham-Denning Model, and Harrison-Russo-Ullman Model. Several security criteria exist for evaluating computer security systems. The common criteria uses a subjective system to meet security needs and a standard evaluation assurance level, EAL, to evaluate reliability. The NIST Risk Management Framework, RMF, establishes an authorization to operate, ATO, issued by an authorizing official, AO, in order to ensure that only systems with acceptable risk levels are used to perform IT operations. It is important to carefully assess each aspect of the infrastructure to ensure that it sufficiently supports security. Without an understanding of the security capabilities of information systems, it is impossible to evaluate them, nor is it possible to implement them properly. The security capabilities of information systems include memory protection, virtualization, Trusted Platform Module, TPM, encryption/decryption, interfaces, and fault tolerance. Exam Essentials. Be able to define object and subject in terms of access. The subject is the user or process that makes a request to access a resource. The object is the resource a user or process wants to access. Be able to describe open and closed systems. Open systems are designed using industry standards and are usually easy to integrate with other open systems. Closed systems are generally proprietary hardware and/or software. Their specifications are not normally published, and they are usually harder to integrate with other systems. Understand open and closed source. An open source solution is one where the source code and other internal logic is exposed to the public. A closed source solution is one where the source code and other internal logic is hidden from the public. Know about secure defaults. Never assume the default settings of any product are secure. It is always up to the system's administrator and/or company security staff to alter a product's settings to comply with the organization's security policies. Understand the concept of fail securely. Failure management includes programmatic error handling, aka exception handling, and input sanitization. Secure failure is integrated into the system, fail-safe versus fail-secure. Know about the principle of keep it simple. Keep it simple is the encouragement to avoid overcomplicating the environment, organization, or product design. The more complex a system, the more difficult it is to secure. Understand Zero Trust. Zero Trust is a security concept where nothing inside the organization is automatically trusted. Each request for activity or access is assumed to be from an unknown and untrusted location until otherwise verified. The concept is never trust, always verify. The Zero Trust model is based around assume breach and micro-segmentation. Know about privacy by design. Privacy by design, PBD, is a guideline to integrate privacy protections into products during the early design phase, rather than attempting to tack them on at the end of development. The PBD framework is based on 7 foundational principles. Understand, trust, but verify. Trust but verify is a traditional security approach of trusting subjects and devices within the company's security perimeter automatically. This type of security approach leaves an organization vulnerable to insider attacks and grants intruders the ability to easily perform lateral movement among internal systems. Know what confinement, bounds, and isolation are. Confinement restricts a process to reading from and writing to certain memory locations. Bounds are the limits of memory a process cannot exceed when reading or writing. Isolation is the mode a process runs in when it is confined through the use of memory bounds. Know how security controls work and what they do. Security controls use access rules to limit the access by a subject to an object. Understand trust and assurance. A trusted system is one in which all protection mechanisms work together to process sensitive data for many types of users, while maintaining a stable and secure computing environment. In other words, trust is the presence of a security mechanism or capability. Assurance is the degree of confidence in satisfaction of security needs. In other words, assurance is how reliable the security mechanisms are at providing security. Define a trusted computing base, TCB. A TCB is the combination of hardware, software, and controls that form a trusted base that enforces the security policy. Be able to explain what a security perimeter is. A security perimeter is the imaginary boundary that separates the TCB from the rest of the system. TCB components communicate with non-TCB components using trusted paths. Know what the reference monitor and the security kernel are. The reference monitor is the logical part of the TCB that confirms whether a subject has the right to use a resource prior to granting access. The security kernel is the collection of the TCB components that implement the functionality of the reference monitor. Know details about each of the security models. Know the security models and their functions. The state machine model ensures that all instances of subjects accessing objects are secure. The information flow model is designed to prevent unauthorized, insecure, or restricted information flow. The non-interference model prevents the actions of one subject from affecting the system state or actions of another subject. The take-grant model dictates how rights can be passed from one subject to another, or from a subject to an object. An access control matrix is a table of subjects and objects that indicates the actions or functions that each subject can perform on each object. Bell-LaPadula subjects have a clearance level that allows them to access only those objects with the corresponding classification levels, which protects confidentiality. BIBA prevents subjects with lower security levels from writing to objects at higher security levels. Clark-Wilson is an integrity model that relies on the access control triplet, that is subject/program/object. Gauguin, Meseguer, and Sutherland models focus on integrity. Graham-Denning focuses on the secure creation and deletion of both subjects and objects. The Harrison-Russo-Ullman HRU model focuses on the assignment of object access rights to subjects, as well as the integrity or resilience of those assigned rights. The common criteria, ISO/IEC 15408, is a subjective security function evaluation tool that uses protection profiles, PPs, and security targets, STs, and assigns an evaluation assurance level, EAL. Authorization to operate, ATO, from the RMF is a formal approval to operate IT/IS based on an acceptable risk level based on the implementation of an agreed-on set of security and privacy controls. Understand the security capabilities of information systems. Common security capabilities include memory protection, virtualization, Trusted Platform Module, TPM, encryption/decryption, interfaces, and fault tolerance. Written lab. 1. Name at least 7 security models and the primary security benefit of using each. Answer. Security models include state machine, establishes the concept of a perfectly secure system, information flow, controls movement of data, non-interference, actions of subjects at one level do not affect the system state or actions of subjects at other levels, take-grant, control passage of rights to subjects, access control matrix, provides a perspective on access of multiple subjects across multiple objects, Bell-LaPadula, protects confidentiality, BIBA, protects integrity, Clark-Wilson, protects integrity, Brewer and Nash, avoids conflicts of interest, Gauguin-Meseguer, protects integrity, Sutherland protects integrity. Graham-Denning provides for secure creation and deletion of both subjects and objects, and the Harrison-Russo-Ullman HRU model manages assignment of rights to subjects. 2. Describe the primary components of TCB. Answer. The primary components of the Trusted Computing Base, TCB, are the hardware and software elements used to enforce the security policy. These elements are called the TCB. The security perimeter distinguishing and separating TCB components from non-TCB components, and the reference monitor that serves as an access control device across the security perimeter. 3. What are the two primary rules or principles of the Bell-LaPadula security model? Also, what are the two rules of BIBA? Answer. The two primary rules of Bell-LaPadula are the simple rule of no read up and the star rule of no write down. The two rules of BIBA are the simple rule of no read down and the star rule of no write up. 4. What is the difference between open and closed systems and open and closed source? Answer. An open system is one with published APIs that allows third parties to develop products to interact with it. A closed system is one that is proprietary with no third-party product support. Open source is a coding stance that allows others to view the source code of a program. Closed source is an opposing coding stance that keeps source code confidential. 5. Name at least 4 design principles and describe them. Answer. There are at least 8 design principles listed in this chapter. Objects and subjects, open and closed systems, secure defaults, fail securely, keep it simple, zero trust, privacy by design, and trust but verify. Please compare your descriptions to the text in each section under the heading Secure Design Principles. Review questions. 1. You have been working on crafting a new expansion service to link to the existing computing hardware of a core business function. However, after weeks of research and experimentation, you are unable to get the systems to communicate. The CTO informs you that the computing hardware you are focusing on is a closed system. What is a closed system? A system designed around final or closed standards. B, a system that includes industry standards. C, a proprietary system that uses unpublished protocols. D, any machine that does not run Windows. Answer. C. A closed system is one that uses largely proprietary or unpublished protocols and standards. Options A and D do not describe any particular systems, and option B describes an open system. 2. A compromise of a newly installed Wi-Fi connected baby monitor enabled a hacker to virtually invade a home and play scary sounds to a startled toddler. How is the attacker able to gain access to the baby monitor in this situation? A. Outdated malware scanners. B. A WAP supporting 5 GHz channels. C. Performing a social engineering attack against the parents. D. Exploiting default configuration. Answer. D. The most likely reason the attacker was able to gain access to the baby monitor was through exploitation of default configuration. Since there is no mention of the exact means used by the attacker in the question, and there is no discussion of any actions of installation, configuration, or security implementation, the only remaining option is to consider the defaults of the device. This is an unfortunately common issue with any device, but especially with IoT equipment connected to Wi-Fi networks. Unless malware was used in the attack, a malware scanner would not be relevant to this situation. The scenario did not mention malware. This type of attack is possible over any network type and all Wi-Fi frequency options. This scenario did not discuss frequencies or network types. There was no mention of any interaction with the parents, which was not required with a device using its default configuration. 3. While working against a deadline, you are frantically trying to finish a report on the current state of security of the organization. You are pulling records and data items from over a dozen sources, including a locally hosted database, several documents, a few spreadsheets, and numerous web pages from an internal server. However, as you start to open another file from your hard drive, the system crashes and displays the Windows blue screen of death. This event is formally known as a stop error and is an example of a blank approach to software failure. A. Fail open. B. Fail secure. C. Limit check. D. Object oriented. Answer B. The blue screen of death, BSOD, stops all processing when a critical failure occurs in Windows. This is an example of a fail secure approach. The BSOD is not an example of a fail open approach. A fail open event would have required the system to continue to operate in spite of the error. A fail open result would have protected availability, but typically by sacrificing confidentiality and integrity protections. This is not an example of a limit check, which is the verification that input is within a preset range or domain. Object-oriented is a type of programming approach, not a means of handling software failure. 4. As a software designer, you want to limit the actions of the program you are developing. You have considered using bounds and isolation, but are not sure they perform the functions you need. Then you realize that the limitation you want can be achieved using confinement. Which best describes a confined or constrained process? A. A process that can run only for a limited time. B. A process that can run only during certain times of the day. C. A process that can access only certain memory locations. D. A process that controls access to an object. Answer C. A constrained process is one that can access only certain memory locations. Allowing a process to run for a limited time is a time limit or timeout restriction, not a confinement. Allowing a process to run only during certain times of the day is a scheduling limit, not a confinement. A process that controls access to an object is authorization, not confinement. 5. When a trusted subject violates the star property of Bell LaPadula in order to write an object into a lower level, what valid operation could be taking place? A. Perturbation. B. Non-interference. C. Aggregation. D. Declassification. Answer D. Declassification is the process of moving an object into a lower level of classification once it is determined that it no longer justifies being placed at a higher level. Only a trusted subject can perform declassification because this action is a violation of the verbiage of the star property of Bell LaPadula, but not the spirit or intent, which is to prevent unauthorized disclosure. Perturbation is the use of false or misleading data in a database management system in order to redirect or thwart information confidentiality attacks. Non-interference is the concept of limiting the actions of a subject at a higher security level so that they do not affect the system state or the actions of a subject at a lower security level. If non-interference was being enforced, the writing of a file to a lower level would be prohibited, not allowed, and supported. Aggregation is the act of collecting multiple pieces of non-sensitive or low-value information and combining it or aggregating it to learn sensitive or high-value information. 6. What security method, mechanism, or model reveals a capabilities list of a subject across multiple objects? A. Separation of duties. B. Access control matrix. C. BIBA. D. Clark-Wilson. Answer B. An access control matrix assembles ACLs from multiple objects into a single table. The rows of that table are the ACEs of a subject across those objects, thus a capabilities list. Separation of duties is the division of administrative tasks into compartments or silos. It is effectively the application of the principle of least privilege to administrators. BIBA is a security model that focuses on integrity protection across security levels. Clark-Wilson is a security model that protects integrity using an access control triplet. 7. What security model has a feature that in theory has one name or label, but when implemented into a solution, takes on the name or label of the security kernel? A. Graham-Denning model. B. Harrison-Russo-Ullman HRU model. C. Trusted Computing Base. D. Brewer and Nash model. Answer C. The Trusted Computing Base, TCB, has a component known as the reference monitor in theory, which becomes the security kernel in implementation. The other options do not have this feature. The Graham-Denning model is focused on the secure creation and deletion of both subjects and objects. The Harrison-Russo-Ullman HRU model focuses on the assignment of object access rights to subjects, as well as the integrity or resilience of those assigned rights. The Brewer and Nash model was created to permit access controls to change dynamically based on a user's previous activity. 8. The Clark-Wilson model uses a multifaceted approach to enforcing data integrity. Instead of defining a formal state machine, the Clark-Wilson model defines each data item and allowable data transformations. Which of the following is not part of the access control relationship of the Clark-Wilson model? A. Object. B. Interface. C. Input sanitization. D. Subject. Answer C. The three parts of the Clark-Wilson model's access control relationship, aka access triple, are subject, object, and program or interface. Input sanitization is not an element of the Clark-Wilson model. 9. While researching security models to base your new computer design around, you discover the concept of the TCB. What is a Trusted Computing Base, TCB? A. Hosts on your network that support secure transmissions. B. The operating system kernel, other OS components and device drivers. C. The combination of hardware, software, and controls that work together to enforce a security policy. D. The predetermined set or domain, that is, a list of objects that a subject can access. Answer C. The TCB is the combination of hardware, software, and controls that work together to enforce a security policy. The other options are incorrect. Hosts on a network that support secure transmissions may be able to support VPN connections, use TLS encryption, or implement some other form of data-in-transit protection mechanism. The operating system kernel, other OS components and device drivers are located in rings 0 through 2 of the protection rings concept, or in the kernel mode ring in the variation used by Microsoft Windows. The predetermined set or domain, that is a list of objects that a subject can access, is the Gauguin-Messeguer model. 10. What is a security perimeter? Choose all that apply. A. The boundary of the physically secure area surrounding your system. B. The imaginary boundary that separates the TCB from the rest of the system. C. The network where your firewall resides. D. any connections to your computer system? Answer: A and B. Although the most correct answer in the context of this chapter is option B, the imaginary boundary that separates the TCB from the rest of the system, option A, the boundary of the physically secure area surrounding your system, is also a correct answer in the context of physical security. The network where your firewall resides is not a unique concept or term, since a firewall can exist in any network as either a hardware device or a software service. A border firewall could be considered a security perimeter protection device, but that was not a provided option. Any connections to your computer system are just pathways of communication to a system's interface. They are not labeled as a security perimeter. 11. The Trusted Computing Base, TCB, is a combination of hardware, software, and controls that work together to form a trusted base to enforce your security policy. What part of the TCB concept validates access to every resource prior to granting the requested access? A. TCB partition. B. Trusted library. C. Reference monitor. D. Security kernel. Answer: C. The reference monitor validates access to every resource prior to granting the requested access. The other options are incorrect. Option D, the security kernel, is the collection of TCB components that work together to implement the reference monitor functions. In other words, the security kernel is the implementation of the reference monitor concept. Option A, a TCB partition, and Option B, a trusted library, are not valid TCB concept components. 12. A security model provides a way for designers to map abstract statements into a solution that prescribes the algorithms and data structures necessary to build hardware and software. Thus, a security model gives software designers something against which to measure their design and implementation. Which of the following is the best definition of a security model? A. A security model states policies an organization must follow. B. A security model provides a framework to implement a security policy. C. A security model is a technical evaluation of each part of a computer system to assess its concordance with security standards. D. A security model is used to host one or more operating systems within the memory of a single host computer, or to run applications that are not compatible with the host OS. Answer: B. Option B is the only option that correctly defines a security model. The other options are incorrect. Option A is a definition of a security policy. Option C is a formal evaluation of the security of a system. Option D is the definition of virtualization. 13. The state machine model describes a system that is always secure no matter what state it is in. A secure state machine model system always boots into a secure state, maintains a secure state across all transitions, and allows subjects to access resources only in a secure manner compliant with the security policy. Which security models are built on a state machine model? A. Bell LaPadula and Take Grant. B. Biba and Clark Wilson. C. Clark Wilson and Bell LaPadula. D. Bell LaPadula and Biba. Answer: D. The Bell LaPadula and Biba models are built on the state machine model. Take Grant and Clark Wilson are not directly based or built on the state machine model. 14. You are tasked with designing the core security concept for a new government computing system. The details of its use are classified, but it will need to protect confidentiality across multiple classification levels. Which security model addresses data confidentiality in this context? A. Bell LaPadula, B. BIBA, C. Clark-Wilson, D. Brewer and Nash. Answer A. Only the Bell LaPadula model addresses data confidentiality. The BIBA and Clark-Wilson models address data integrity. The Brewer and Nash model prevents conflicts of interest. 15. The Bell LaPadula multi-level security model was derived from the DoD's multi-level security policies. The multi-level security policy states that a subject with any level of clearance can access resources at or below its clearance level. Which Bell LaPadula property keeps lower-level subjects from accessing objects with a higher security level? A. Star security property, B. No write-up property, C. No read-up property, D. No read-down property. Answer C. The no read-up property, also called the simple security property, prohibits subjects from reading a higher security level object. The other options are incorrect. Option A, the star security property of Bell LaPadula, is no write-down. Option B, no write-up, is the star property of BIBA. Option D, no read-down, is the simple property of BIBA. 16. The BIBA model was designed after the Bell LaPadula model. Whereas the Bell LaPadula model addresses confidentiality, the BIBA model addresses integrity. The BIBA model is also built on a state-machine concept, is based on information flow, and is a multi-level model. What is the implied meaning of the simple property of BIBA? A. Write down, B. Read up, C. No write up, D. No read down. Answer B. The simple property of BIBA is no read down, but the implied allowed opposite is read up. The other options are incorrect. Option A, write down, is the implied opposite allow of the star property of BIBA, which is no write up. Option C, no write up, is the star property of BIBA. Option D, no read down, is the simple property of BIBA. 17. The common criteria defines various levels of testing and confirmation of systems security capabilities, and the number of the level indicates what kind of testing and confirmation has been performed. What part of the common criteria specifies the claims of security from the vendor that are built into a target of evaluation? A. Protection profiles. B. Evaluation assurance levels. C. Authorizing official. D. Security target. Answer D. Security targets, STs, specify the claims of security from the vendor that are built into a target of evaluation, TOE. STs are considered the implemented security measures or the I will provide from the vendor. The other options are incorrect. Option A, protection profiles, PPs, specify for a product that is to be evaluated, the TOE, the security requirements and protections, which are considered the security desires or the I want from a customer. Option B, evaluation assurance levels, EALs, are the various levels of testing and confirmation of systems security capabilities, and the number of the level indicates what kind of testing and confirmation has been performed. Option C, an authorizing official, AO, is the entity with the authority to issue an authorization to operate, ATO. 18. The authorizing official, AO, has the discretion to determine which breaches or security changes result in a loss of authorization to operate, ATO. The AO can also issue 4 types of authorization decisions. Which of the following are examples of these ATOs? Choose all that apply. A. Common control authorization. B. mutual authorization, C, denial of authorization, D, authorization to transfer, E, authorization to use, F, verified authorization. Answer: A, C, and E. The four types of ATOs are authorization to operate, not listed as an option, common control authorization, authorization to use, and denial of authorization. The other options are incorrect. 19. A new operating system update has made significant changes to the prior system. While testing, you discover that the system is highly unstable, allows for integrity violations between applications, can be affected easily by local denial of service attacks, and allows for information disclosure between processes. You suspect that a key security mechanism has been disabled or broken by the update. What is a likely cause of these problems? A, use of virtualization. B, lack of memory protections. C, not following the Gauguin-Messager model. D, support for storage and transmission encryption. Answer: B. Memory protection is a core security component that must be designed and implemented into an operating system. It must be enforced regardless of the programs executing in the system. Otherwise, instability, violation of integrity, denial of service, and disclosure are likely results. The other options are incorrect. Option A, the use of virtualization, would not cause all of those security issues. Option C, the Gauguin-Messager model, is based on predetermining the set or domain, that is, a list of objects that a subject can access. Option D, the use of encryption, is a protection, not a cause of the security issues. 20. As an application designer, you need to implement various security mechanisms to protect the data that will be accessed and processed by your software. What would be the purpose of implementing a constrained or restricted interface? A, to limit the actions of authorized and unauthorized users. B, to enforce identity verification. C, to track user events and check for violations. D, to swap datasets between primary and secondary memory. Answer: A. A constrained or restricted interface is implemented within an application to restrict what users can do or see based on their privileges. The purpose of a constrained interface is to limit or restrict the actions of both authorized and unauthorized users. The other options are incorrect. Option B describes authentication. Option C describes auditing and accounting. Option D